the 1970s, Derek Ager wrote a slim little volume called The Nature of the Stratigraphical Record. Such a great title. In it, he argued that there were strong secular trends in geology. A competent geologist, he argued, could make a fairly accurate stab at how old rocks in a distant mountain range might be when seen from afar, either while driving down the highway in Nevada or peering across the terrain of the Alps. There were a couple of clues. First is the change in bed thickness in sedimentary rocks. Paleozoic sediments are often thin-bedded, whereas Mesozoic strata are often much more massive. This difference in bed thickness has been explained by Mary Drozier as due to the evolution of increasingly efficient burrowing by animals that homogenize thin-bedded sediments into thicker beds. Second, Ager suggested that Paleozoic rocks are mainly gray, whereas Mesozoic and younger rocks are white, tan, or red. Now here I'll explain why this secular trend in sediment color exists. I think it has to do with oxygen. The expansion of animal ecologies away from the sea floor to become plankton or to establish themselves in epifaunal or infaunal tiered communities looks a bit like the diffusion of perfume in a room. Animals have expanded their habitats as a means of exploiting resources that are underutilized or to avoid effort of competition where resources are closely fought. These patterns raise the question of whether evolution is just a diffusional process, where directionality is partly set up by the strength of competition, or whether there are other processes going on, such as changes in hard limits to evolution, that open up new possibilities for animal evolution that were unavailable in the past. One potential hard constraint is the oxygenation history of the Earth. The idea of constraints is that evolution works within architectural and energetic limitations on animal bodies and the limitations imposed by the environment. These limitations or constraints may be so tight that there are only a few ways to do things. We have hints of such strong constraints in the wealth of examples of so-called convergent evolution, in which animals have independently arrived at similar design solutions to common problems. A case in point, to which I'll return later, is the amazing similarity between saber-toothed cats, like California's state fossil Smilodon, and the nimbravid carnivores, who happen to be unrelated to cats, that independently evolved sabers and the reduced shearing tooth set of modern cats. Presumably, convergence is not typically so precise unless there were strong common selective forces at work. So now let's examine the history of oxygenation of Earth as a possible hard constraint on biotic evolution, and an explanation for Ager's observations of sediment color. Oxygen limits how physiologically active animals can be, and that can affect animal body size, motility, brain function, and many other aspects of ecology. As a personal example, my cousin Jim, who is a pilot, once did a pressure test, where you sit in a sealed chamber and you're asked to do some menial task like simple adding and subtraction of colored numbers. The chamber crew slowly lowers the oxygen pressure in the chamber while you're reading, and this simulates the loss of cabin air pressure when you are flying a plane. Jim tells me that the amazing thing was not the gradual loss of oxygen, which he hardly noticed. Instead, the surprise was at the end of the experiment. As the oxygen level rose once again, suddenly his color vision returned. He had not noticed its loss, but in fact his brain functions, eyesight, and ability to calculate had all taken a big hit while the oxygen levels were low. I'd say this is a lesson for what animals were capable of when the oxygen levels of the past atmosphere was lower than that of today. There were things that they simply could not do because they did not have enough metabolic energy to do them. The history of oxygen is not that easy to work out, unfortunately, since we have no direct way to measure oxygenation in the past. There are lots of methods that are all kind of so-so, ranging from the appearance of banded iron formations mentioned a while back, which show us that there was some free oxygen, to molybdenum isotopes and iodine-calcium ratios that make a stab at the amount of O2 around. These methods suggest that after the Great Oxygenation Event 2.5 billion years ago, when O2 levels may have been maybe 0.5% of present levels, oxygen rose to 1 to 2% present atmospheric level, also called PAL, in the Neoproterozoic, say 700 million years ago. These numbers are not that well constrained, but clearly much less than today. The record suggests that oxygen was between 15 to maybe 50% PAL by Ediacaran time, maybe 20 to 60% PAL in the early Paleozoic, and 40% PAL or more in the Devonian when Earth starts to make coal. To my mind, a particularly good lower bound estimate of oxygen comes from the first evidence for smoldering fire in the Devonian. Experiments show that oxygen must have been at least 17% O2 in the atmosphere to get sustained fire, namely about 80% PAL. To put this into modern context, the top of Mount Everest has about 33% oxygen available at sea level, roughly what animals would have had in the early Paleozoic. So you would need an O2 tank to visit the Cambrian. Things may actually have been worse than those numbers suggest, because the ocean need not look like the atmosphere in terms of its oxygen content. Even if atmospheric O2 was 80% of today in the Devonian, the ocean could still have had considerably lower dissolved oxygen than that, since oxygenation of the ocean is a balance between consumption of O2 by respiration and renewal of O2 by mixing with the atmosphere. Now, as it happens, marine animals in the Paleozoic are ecologically consistent with low dissolved oxygen in the ocean. They are mainly sedentary critters, brachiopods, sponges, corals, that do not move, very much at least, and do not use very much power or need very much oxygen. Furthermore, Paleozoic sediments tend to be dark-colored and sulfitic, typical of those formed under modern suboxic waters, suggesting that oxygen had been consumed completely in bottom sediments and perhaps reduced to very low levels near the seafloor as well. Now, this situation changes drastically in the Mesozoic, 250 million years ago. There we find lots of highly mobile animals, squids, fish, burrowing clams, and marine reptiles. A lot of these are bigger and more meaty than their Paleozoic forebears. A brachiopod, for instance, may be the size of a clam, but the clam is stuffed with muscle tissue, gills, and guts, whereas the brachiopod shell is mostly empty. What? Brachiopods use the shell as a filter feeding chamber, and it's mostly filled with seawater, whereas the body is a pea-sized thing at the back of the shell. So it's worthwhile to dig up a clam and eat it, but the same cannot be said for a brachiopod, even if they were not toxic, which they are. The Mesozoic story is that suddenly animals start to invest in being big, active, and making lots of expensive tissue. Predation skyrockets as a result. Suddenly the fossil record is full of shells with drill holes, pavements of crushed clam shells, and ammonoids abandoning their heavy shells to go bare as squids. Predators also tool up with heavy claws for crushing prey, muscled bodies for fast swimming, and the ability to burrow fast and deep after buried prey. All this predation and defense is energetically costly. You don't do these things if the energetic resources are not there. Now, notably, there is geologic evidence that one of the triggers was oxygen. Those gray sediments I mentioned before that indicate hypoxic conditions in Paleozoic sediment, well, they're gone or nearly so in the modern ocean, replaced by an abundance of sediments with oxidized colors, white, tan, brown, and red. The sediment is now mostly oxic, a situation that becomes evident about 200 million years ago. So oxygen is probably an environmental constraint that prevents a completely stochastic diffusional process, like perfume filling a room, of animals discovering new habitats in marine ecosystems. Evolution of animals with active metabolisms was simply not possible in a low oxygen world. It is also likely that animals get big in the Ediacaran because the oxygen constraint had been at least partly weakened by rising oxygen concentrations to make it possible to be a big animal instead of a dinky planula-like thing of the Neoproterozoic. While the Cambrian is unlike today in that animals were living in a low oxygen world, the constraint had been lifted enough to make it possible to be a predator and even to start to mine sediment for food. By the Mesozoic, 200 million years ago, the ocean had become much better oxygenated, and animals responded by becoming much bigger, meatier, faster, and more vicious predators. The bottom line is that in the end, the planetary metabolism is jacked up as the ocean becomes better oxygenated and the atmosphere is too. The whole biosphere recycles a lot more nutrients, more CO2, and more oxygen in the Mesozoic and Cenozoic than it did in the past.